Welcome to the first lecture of the course Crystal Symmetry, X-ray Diffraction and Physical Properties. As the name implies, the course has three components. So, what are the three components? The three components are: first is crystal symmetry, the second component is X-ray diffraction, and the third component is physical properties. The course, looking at these three components, the first component perhaps is the most important component and it will take more than 50% of the course, and the remaining will be after completing this. It is absolutely important to do crystal symmetry first before we can take on X-ray diffraction and physical properties. Now, what are some of the salient features of the three components? The salient features, for example, of crystal symmetry, in a more general this thing, it is also called as crystallography. And most students of sciences and engineering would have done an basic course of material science in which some part of crystallography is included. But we will be going into those starting from the basic components. We will take it to a much deeper level of crystallography and symmetry. In fact, symmetry is the basis of crystallography. But before I put down, what are the things that I am going to do today, let me look at what I am going to do in X-ray diffraction. Well, one of the things we will look at is analysis of crystal structure. I will also introduce this concept called reciprocal lattice in this. And a brief overview on experimental techniques. And in physical properties, we will look at properties like conductivity, piezoelectricity, elasticity, among others. And we will look at first their tensor representation, and what is the role of crystal symmetry. Now, coming to crystal symmetry, in today's lecture, in fact starting from today, in the next 2-3 lectures, I want to introduce three key concepts. The concept of what is a lattice, what is a crystal, and what is a motif, which is also called as basis. So, these three are key concepts to begin with, and in fact there is a lot of confusion. So, first we need to get rid of all of those confusions that have been generated in an elementary course on material science, where crystallography is covered in a very quickly without really going into the depth of crystallography itself. For instance, let us consider first the lattice. So, if I were to say lattice, what is a lattice? Lattice is basically some kind of an arrangement of points. So, if I want to put it into words, I could put it a regularly spaced arrangement of points. And these points could be, we can consider in 1 dimension, in 2 dimension or 3 dimensions. Now, if I were to look at the crystal, I would say a regularly spaced arrangement of atoms. So, let us look at these two concepts, and this again in the case of atoms as well, it is 1 dimension or could be 2 dimension or 3 dimensions. Now, if I look at these two definitions here, the only difference you find is in one case, in the case of lattice, it is points, in the case of crystal, it is atoms. And because of such a similar definition, this produces a lot of confusion as well as misconceptions. So, some of the misconceptions we will come across as we go along in this course, and my attempt would be to remove all those misconceptions that have crept through. And these misconceptions have crept through partly because in a very basic material science course, there is a small topic on crystallography, and in order to attempt it to make it simple enough to understand, some of the things actually then become wrong, some of the concepts become wrong. And in fact, in many of the even the basic texts of material science for an undergraduate class, they carry some wrong notions, and my endeavor would be try to remove all those misconceptions regarding crystallography. So, now if I look at lattice and crystal, if I look at the similarity first, what is the similarity in the two cases? The similarity is that they have a geometrical periodicity. And now let us focus on the differences. Differences, case of lattice, it is an abstract geometrical entity, and in the case of crystal, this is a physical entity. So, lattice, which is an abstract geometrical entity, if I look at a lattice, it will have, so there are no physical properties associated with the lattice. In the case of crystal, we have physical properties. So, if I look at it, a crystal will have some kind of a conductivity, some crystals may show piezoelasticity, it may show elasticity, it may show many other properties like density and so on. So, remember, this is a crucial difference. One case, that is an abstract entity, only a bunch of points in space. In the second case, they are atoms. But then the next question that arises is, then because these two things are confused so often with each other, the lattice and crystals are used interchangeably, which leads to all kinds of confusion and misconception. So, here my job is to make it very clear that a lattice is a different thing, a crystal is a different thing, but the question that comes is, what is the relationship between the lattice and the crystal? So, we come to the relationship. Between lattice and crystal. So, let us try to understand this. Here, what is going to become important is, so the important idea, what is important to draw a relationship between lattice and crystal is a third key concept that I had introduced, motif. Or basis. So, now before we try to understand this relationship, I would like to first give a very clear definition of what is a lattice. Lattice, sometimes it is also called as a point lattice. And as I had indicated earlier, this could be 1 dimensions, 2 dimensions, or 3 dimensions. Let us take an example in 1 dimension first. So, let us take a 1 dimension example, that I have a row of points which extend to infinity in both directions. These are, as I had said, what should these points obey now? This is a row of points. Lattice is a regularly spaced arrangement of points, which means that the spacing between the points have to be same. And the lattice itself can be defined by a vector, and let me call that as A, the vector A, what is also called as a translation vector. This vector connects one lattice point to the next lattice point. Now, I can think of a vector NA, where n is a integer, which means n can go from minus infinity to plus infinity. So, n could be minus 3, minus 2, minus 1, 0, 1, 2, 3 and so on, and they go from minus infinity. So, here I have plus infinity and out here I have minus infinity. And you can see that this particular vector NA is also called as a lattice translation vector. So, this is a lattice translation vector, I can call it, let us say, R. So, R is equal to NA. What this means is, by changing different values of n, I can visit every lattice point, or I can generate this one dimensional lattice by choosing different values of n. Another definition of a lattice, which is often written in books, is that each lattice point has identical environment in the same direction. Though of course, in this case, in the one dimensional case, this same direction is only one direction we have, but once I go to 2 dimensions and I go to 3 dimensions, then I will have infinite number of directions. So, in any direction you were to travel from one lattice point to another lattice point, you should see equally spaced lattice points. Let us take another example in the sense of now going to 2 dimensions. So, a lattice in 2 dimensions. Let me just try to draw one 2-dimensional lattice. You can imagine that I have shown a small part of an infinite lattice in all directions. So, these set of points are spread in both. You can imagine that this is, let us say, the x direction and this is the y direction. So, they are along x going from minus infinity to plus infinity, along y minus infinity to plus infinity. So, you have an infinite lattice. Here, now if I have to look at a translation vector, so I can let me call this as A and the second vector as B. Now, if I have to write a lattice translation vector for this, so the lattice translation vector R, I can write in terms of 2 integers. Let us say n1 A plus n2 B, where both n1 and n2 are again integers. Again, this lattice translation vector, starting from any lattice point, one can visit any other lattice point, or this lattice translation vector can generate the entire infinite lattice. Now, I always keep saying that the lattice is infinite, because the very definition of the lattice, if I look at this particular definition, identical environment in the same direction. So, for example, if I have to travel from here to here, I get some spacing in this case will be B, again B and so on, same spacing. If I were to move from this lattice point to this lattice point, now this will be a different spacing, and this from second to third, it will be a same spacing as before. So, here if it is B, here it is going to be some spacing R, which will be a function of both A and B. Now, one can even think of a direction like this. Again, you will get equally spaced lattice point, but with a different spacing. So, this definition, this is what it means, identical environment in the same direction. Another thing is that we keep saying it is an infinite lattice. We keep saying it is an infinite lattice because the very definition of the environment being identical implies that if it was a finite lattice, for example, if I consider this point where now I have come to a boundary, it is a finite lattice, then this point does not have the same environment. If I were to travel in this direction, it does not see any lattice point here. So, the very definition of identical environment in the same direction implies that the lattice has to be necessarily infinite. So, I hope this makes it clear what is a lattice of points. So, one thing is there. So, this is where one can say that what is the defining property of a lattice. The defining property of a lattice is in fact a symmetry which is called as translation symmetry. If let us say an arrangement of points do not have this translation symmetry, then it cannot be called as a lattice from a crystallographic point of view. So, I think it will be useful if we take one example, which is an orderly arrangement of points, but is not a lattice. Let us consider that. In order to draw the lattice points, I am first drawing regular hexagons. It is like a honeycomb structure. Okay, this way you can imagine that this is a space filling thing and again extending to infinity, and let me put lattice points at the corners of this hexagons. So, I have put this bunch of points and it is a perfectly regular arrangement of points, but I say that this is not a lattice. Now, why do I say this? We again go back to this definition of the lattice, identical environment in the same direction. So, let us see, let us identify a few lattice points. So, let me identify a lattice point here as A, another lattice point as B. Now, consider the translation from the lattice point B in this direction. So, let us say this translation vector is A in a given direction, and we go from B to a lattice point C. Now, consider the same translation from the lattice point A. In this case, this translation does not end at a lattice point, which means that the environment of points in the same direction at B and A are different, and that is the reason why we will not call this as a lattice. So, I hope this definition of a lattice then becomes clear, and at this point the next topic that we will look at is a crystal and how the crystal is related to the lattice and motif, how they get the two relations, which will be a subject of the next lecture.